Welcome back for a video on the derivative of a function at a point. So this material is covered in section 1.3 of our textbook, and here you can see some of the goals that I set out for us for after we watch this video and read this portion of the textbook. We'll begin with an example. So imagine we had tossed somebody. We don't want to put ourselves in this situation. Imagine someone tossed a penny off the top of a building, and that its height in feet at a time t in seconds was given by this function s of t. Now, it's an old question at this point, settled last week, for how to determine the average value of the velocity, that is the average velocity over an interval. So what I would like you to do is maybe pause the video and in two different ways write down the average velocity of an interval starting at 2 and ending at a variable point. For one, when the end of the interval is at b, and for 2, when the interval lasts for h seconds. So give it a shot. And we should find that our answers look like this. Now, if you're not sure how I got that, maybe double check your work and go back and check a previous video or send me an email if you're really stuck. But we can then go on and ask questions about the instantaneous velocity at t equals 2. And the approach is the same for either of these expressions. We want to let that interval shrink. So whether it's by taking the endpoint and moving it towards the start, that is taking the limit as b goes to 2, or by just letting the interval shrink to a width of 0, that is taking h and letting that go to 0. In either case, we're taking a limit, so we can compute those both here. I'll use some factoring and some canceling to evaluate those limits. And in either case, we find that the instantaneous velocity minus 32 feet per second. Of course, it's negative because the penny is falling. And this motivates our definition. This is going to be huge. We'll be talking about this for most of the course. The derivative of a function at a point. So if we've got a function who is defined at a point x equals a, this limit, which should look pretty familiar, is known as the derivative at the point x equals a. So when we read this, we might say f prime of a, or the derivative of f at a. And there's three ways that we'll think about derivatives interchangeably. One is this limit definition, the limit we just wrote down. 2, the instantaneous rate of change. And 3, graphically, as the slope of a tangent line, as we saw earlier in the course. So, some examples. 1, we could compute a derivative algebraically, that is using the limit definition. And this is what we just did in that first example. So we didn't call it the derivative at that point, but really what we found is that s prime of 2 is equal to minus 32. The derivative of s at the point 2 is minus 32. How about numerically using that limit definition? So here's a function involving sines and cosines, and we can set up the limit. We don't want to do this by hand, so let's head over to GeoGebra and do it there. Here's the GeoGebra page where we've got our function f of x graphed. We can zoom in or out and see it's a pretty funky graph here. But the question at hand is, what is the derivative when x equals 0? Algebraically, we don't really want to try this, to mess around with limits involving sine and cosine right now. In terms of the slope of the tangent line, we probably could estimate that. At this moment, let's just say, well, the slope of the tangent line will be positive. So if we get a negative value, we know we did something wrong, but we should expect our derivative to be positive. Now, we do want to take a limit, but it's not a limit of f. Remember, what we want is a limit of the average value. So let's do this. The average value looks like this equation. And we want to know, we don't really care what it looks like. We can get rid of the graph. We want to know what is the limit of this thing as h goes to 0. So we'll do what we did in a previous video. We'll click here and ask for a table of values. We want the limit as h goes to 0. So here I've picked some values that hug pretty tightly around 0. It's calling these values for x. That's okay. And if we look at our values, we want to know what's happening when this gets really close to 0. And from the left and from the right, we see these values are agreeing at least up to the third decimal place. And that's good enough for us. If they weren't, we could go back and set the bounds to be even tighter, or that the steps were even tighter until we did get here. So we can round off both of these so they match and say that is our derivative. And so this is what we found our limit to be, our derivative to be approximately. And how about applying the graphic definition? So we'll answer lots of questions like this one throughout the course, but here's a function f of x, and I would like to know the equation of its tangent line at a point, specifically at the point where x equals 1/2. So I'll leave it for you to use one of the methods above and find that f prime of 1/2, the derivative of f at the point 1/2, is equal to 1/4. Remember, the derivative is the slope of our tangent line. The tangent line is what we're after, so we know that the slope of that line is 1/4. But if you remember back to your algebra class or your pre-calc class, to define a line, we need a slope and a point. So where can we find this point? Well, you can use GeoGebra to do this, or you can try to sketch it by hand, but our function looks something like this when we graph it. Or we can just plug in x equals 1/2 and find that f of 1/2 is minus 1/8, or minus 0.125. So that's the point we need. And we can proceed one of two ways. One, using point slope form, which looks something like this, where x1 and y1 is some point on the line, and m is the slope. And, well, what we have here, you can leave your answer just like that. That is the equation of the tangent line. Perfectly good. It's probably not what you're used to doing. I know slope-intercept form for a very long time was my first instinct, so let's try that. So slope-intercept form, also known as y equals mx plus b. M is the slope, b is the y-intercept. Here, we don't know that, but we do know a point that we can plug in for x and y. So our strategy will be plug in the x value we know, 1/2, the corresponding y value we know, minus 1/8, and then we can solve for b. So we do that here to find that b equals minus 1/4, and then putting it all together, y equals mx plus b, with the m we know, the b we know, and here's the equation of our tangent line. Why don't you head over to GeoGebra, graph these two together, and see how the tangent line fits right in. Nice job, and I will see you in class next time.